Now I would like to show you one very useful trick that allows to compute even complicated integrals. Namely, if the integration interval is symmetrical and the function is odd, then the integral is equal to 0. Let me explain this in more detail. First, let's revise what we mean by odd. An odd function, an example of an odd function is, say, x2 cube. The graph looks like that, and it is symmetrical with respect to the origin. It is the same story if the exponent is another odd integer. And it doesn't have to be of this power form. It is completely enough when f at minus x is minus fx. An example of an odd function that is not in this form is, say, sine. Sine looks like that, and the graph is again symmetrical with respect to the origin. And if you change the sign of the argument, then it is equal to the opposite value of the original function value. So this is the definition of the odd function. And if this is true for all x in the domain of definition, then we say the function is odd. And even function, an example of an even function is, say, x to 4. Now the graph is symmetrical with respect to the y-axis, and the definition is that we want f minus x to be equal to fx directly. No minus here. So this is the definition of the even function, this is the definition of the odd function. And we have seen that when differentiating, the derivative of an even function is an odd function and vice versa. The derivative of an odd function is an even function. We have even proven this result as a theorem. Well, and integrating is the opposite operation to differentiating. So we might expect that something in this sense is there also valid. If we integrate x to 4, we have x to 5 plus c. This will be an odd function provided c is 0. So in general, we cannot conclude that we cannot conclude that the integral of an even function is odd, only under the appropriate choice of the constant c. But if we integrate an odd function, then we have, in this case, x to 6 divided by 6. And this is, fortunately, an even function for any c. So we can say that if f is odd, then the antiderivative is even. And this is very useful because then the definite integral, but this is useful only for symmetrical interval, when we integrate not from general A to general B, but from minus A to plus A. So once again, this will be very, very useful under these two conditions. The function is odd. That means this is true. And we integrate from minus a to a. The integration interval must be symmetrical with respect to the origin. because then we have antiderivative at a minus antiderivative at minus a. But for an odd function, the antiderivative is even. So f minus a is equal to a. So we subtract two equal numbers, which is always 0. And this is true even for complicated functions f. The function f may be so complicated that we are not able to find the antiderivative. But just from the knowledge that f is continuous and odd, this integral is equal to 0. And we are done. This is the exact result. Let me show you this by two examples. When the antiderivative can be found and when the antiderivative cannot be found. So the easy example, consider, say, sine, for example, an integral from minus pi to pi. Then the antiderivative for sine is minus cosine. And you see, odd function as the integrand, even function as the antiderivative. So we have cosine at pi is minus 1, and minus is plus 1, minus, and cosine at minus pi is the same, so we must subtract the same number, and it is 0. It can be visualized by this graph. Let me sketch this in better scale. If the function, if the integrated function is odd, then the graph is symmetrical with respect to the origin. So this area has a counterpart on the left, and if the function is positive, that means this contributes with some positive contribution to the result, and then this is negative. It contributes with a negative value, and vice versa. Actually, this is true even for any odd function. If it is complicated like that, for positive x, then it must be for negative x like that, and if this is the positive contribution to the definite integral, this is the contribution of the same size but opposite sign, and together it gives 0. So let me show you one perhaps surprising result. Consider integral from minus 3 to 3 x times e to cosine x squared. I tried to prepare a function for which we cannot find the antiderivative. But if you see symmetrical interval, there is a hope that the function will be odd, and then we know the result, namely 0. Is this function odd? Well, it's quite easy to show that it is. X squared is definitely even, because if you change the sign of x, the same result. So if you change the sign of x, x squared gives the same output. And then, no matter what you do with this output, whether you evaluate cosine, exponential, and so on, this all will be also even, because at the very beginning, the change of sign is forgotten. And x alone is odd. And if you multiply an odd and an even function, the result is odd. Because if you change the sign of x, no change here, this is the opposite result. So the result is just the opposite number. And this function is odd. The integral is symmetric from minus 3 to 3, so we know for sure that the result is 0. We don't have to try to find an antiderivative, which may be difficult or even impossible. So this is a very, very important trick. And what about the even function? Well, there is also slight simplification, but far less useful. If f is even, then the antiderivative is odd. And if we have some function like that, then instead of integrating from -a to a, it is completely enough to integrate from 0 to a and multiply by 2, because the area of the parts on the right and on the left are the same. So if we integrate an even function over a symmetrical interval, we can integrate from 0 to a and multiply by 2. This is the small help, but this is the big help.